Hey there, let's dive into section 3.2A. We're talking about radians, which we started to talk about in class, but let's talk about it a little bit more. An angle is, remember, in standard position when the vertex coincides with the origin and one way corresponds with the positive x-axis. That basically means that it starts here. Okay, if it's in standard position, it starts at the initial ray. Okay, so if it's there at the initial ray, and we know that this starts at 0 degrees, remember going in counterclockwise motion, we know this is 90 degrees, this is 180 degrees, this is 270 degrees, and then back around the circle is 360, okay? So this first part, draw a positive 45-degree angle in standard position and label the initial and terminal ray. So if this is the initial ray here, we know positive 45 degrees is going to go counterclockwise halfway to 90, which is 45 degrees, which also tells me that this is the terminal ray because that's where we end, okay? If it says draw a negative 225-degree angle, I know I'm still going to start at 0 at the initial ray, but instead of going counterclockwise, I'm going to go clockwise. So this would be negative 90, this would be negative 180, and this would be negative 270. So negative 225 is going to be halfway to that negative 270. So this is negative 225. And this would also be our terminal ray. Okay. And then it says label the quadrants 1, 2, 3, and 4. Remember, we started in the upper right-hand quadrant. We call this quadrant 1. And then we go counterclockwise from there. So here's 2, 3, and 4. Those are your quadrants. So let's talk about angles that are in standard position. Remember, standard position always starts from that x-axis in the origin. So remember, we always start from here. So if that's true, I know an angle that touches C, we could say is CDB. That's from here to here. So angle CDB, where the initial ray is right here on the positive x-axis is DC. We call that a ray. And the terminal ray would be DB. We can also say there's another standard position angle starting here, and we can see it right here. So that's going to be angle CDA, where the initial ray is again DC, but our ray ends at DA. But in moving forward, we're not going to be measuring things in degrees anymore. We're only going to be dealing with radians. Okay, we're getting ready for calculus, so we're only dealing with radians, which we've been talking about, we talked about today, okay? So we're going to be formalizing the definition of radian in a minute, but let's go ahead and keep talking about how do we sketch these things. So using the circle in the sketch, we're going to sketch an angle with a terminal ray or an ending ray in quadrant 2. Remember, this is our quadrant 2 here, that upper left-hand quadrant. The rays of the angle will be touching the circle. The fancy way of saying this is that the angle, or that the arc of the circle is subtended by the angle. So let's say this is theta. So let's draw an angle starting at that initial ray, let's say here, okay? So this is theta. Okay, there's my angle. But the arc that it intercepts, so that would be from here on the circle, this is the arc. This is our subtended arc. So theta would equal the length of the arc on the circle divided by the length of the radius, okay? Where we know that this distance here is the radius. Also, we see that here and here and here, but also here, okay? From the center to the edge of the circle is always a radius. So what is a radian? So we know that a radian is when one radius of the circle is on the circle. So this is, remember, 1 radius, and this is 1 radian. And that's because it's on the circle. So if we're measuring in radians, this theta equals 1 radian. Okay, and the arc that it intercepts or is subtended by is also 1. Okay, so I'm going to ask you this. Can you estimate how many radians are in one circle? Maybe if you were paying attention today, put in your estimate and we'll see if it works. So the second part, if the figure on the angle is in standard position and a circle has a radius of 4 here, so we see this radius of 4, the length of the minor arc, remember minor arc means less than a half a circle, is subtended by the angle is 8.796. So we see the subtended arc is this 8.796. Find the measure of the angle. So they're saying, hey, find theta. Well, we know theta is the arc divided by the radius. So in this case, the arc is 8.796 divided by the radius we said was 4. If I put that in my calculator, we get 2.199, and that's because it's an angle. We know that that's measured in radians. Okay, so part 3, if an angle measure, so if I'm looking at this angle measure, we call that theta, is 1.4 pi radians, and the radius of the circle is 2.7. What's the length of the arc? So we're looking for the arc. So remember, again, I know if theta equals S over R, I can move this around. So if I want to get S by itself, let's multiply it by R. So then I get S equals theta times R. Well, I know S equals theta, which is 1.4 pi, times the radius of 2.7. So we get this is in our calculators, this is approximately 11.875. And that's our arc. I'm going to have you go ahead and push pause right here and try this one on your own for number 4. All right, let's see if you got the same thing as me. So again, we're given the measure of the angle here in radians, and what the arc length is S. What's the radius? So if I know theta equals S over R, how do we find R? Well, R is here, so I'm going to multiply R to the numerator, but then get it by itself, so we're going to divide by theta. So we get R equals S over theta. So here we go. R equals S, which is 3.125 pi, divided by theta, which is 0.625 pi radians. We see here that the pi's cancel, and in your calculator, 3.125 divided by 6.25 is approximately 5. All right, moving on. Unit circle. So remember, a unit circle means that it's a circle with a literal radius of 1 unit. And that's why we call it the unit circle and not units, plural, because it's just 1 unit. So if I'm looking at that, remember that this unit circle, if we have a unit circle, that also means that whatever theta is the subtended arc because it's a radius of 1. So here, remember these points. If this is a radius of 1, that means we go over 1 up 0, over 0 up 1. At the top, on the left here, we get -1, 0. And at the bottom here, it's 0, -1. With that said, let's move on. Remember, this is really important to remember with a unit circle. For a unit circle, we also know that if the circumference is 2 pi r, if r equals 1, then the circumference, or 1 revolution, represents just 2 pi radians, which is approximately 2 times 3.14 is 6.28 radians. Okay, was this your estimate from before? I hope it was, because we did that in class. That means half of the revolution is 3.14, or pi radians. And a quarter of that is going to be half of that, or pi over 2, aka 1.57 radians. Okay, so if I'm measuring the unit circle in radians instead of degrees, this is 0 radians. Here's pi over 2 radians. Here's pi radians. Here's 3 pi over 2. And then back at the full circle is 2 pi radians. So let's finish this up. We're going to give an estimate of how many radians the angle represents. So if I'm looking at this angle here from standard, positive, we look from here to here. I know that, okay, in radians, if this is 1 pi, here's 2 pi. I know it's got to be more than 1 pi, right? And I know this is 3 pi over 2, which is the same as 1.5 pi. So this I'm going to say is approximately about 1.1 pi radians. And lastly, This last one, number 6, it says the angle in the standard position that shares a terminal ray differ by an integer of revolution. So what on earth does that mean? So if I've got 4.3 pi, remember a full circle is 2 pi. So if I go all the way around, that's 2 pi. If I go another 2 pi, we get 4 pi. So where would 4.3 be? Well, I know if this is half, if I know, whoopsie, from here to here is half a pi. So I know 4.3 would be about right here, okay? So this tells you that it's in quadrant 1, is at 4.3. All right, that's it for now. See you back in class.